Let me just give a very brief introduction. So this is our, I think, second seminar for the series of the AI Planning Institute seminar series. So this was kind of a part of our planning activity for a large-scale AI institute. And today we have Dr. Feng Yan and Dr. Feng Yan is currently assistant professor in the Computer Science and Engineering Department at UNR. He's the director of the Intelligent Data and System Lab at UNR. And Dr. Yan received his both master and PhD degree in computer science from the College of William Mary. And he worked at Microsoft and HP labs. And his recent research focus include machine learning and cloud, high performance computing, storage, as well as a lot of cross-interdisciplinary topics such as data-driven research and also AI material science engineering. His team has been publishing a lot of papers in the most prestigious venues in machine learning area and computer systems, and he and his student receive a lot of work. So today he's gonna tell us his very interesting work on this aspect.
Okay, thank you for the introduction. And good morning, everyone. Thank you for attending my talk, especially on a Friday morning when the election is still going on. So I thought most of you are taking sabbatical this week. So I would also like to thank Nick, Yang, Max, and other fellows from our AI Institute project for inviting me to this talk. Okay, so to begin with, just a quick overview of my research background. So I direct the Intelligent Data and System Lab at University of Nevada, Reno. And this shows you a very brief overview about our lab's short-term and long-term research focus. So our long-term focus is to design methodologies and systems that are intelligent, efficient, robust, and dependable. And we also love this interdisciplinary research topics, and that's actually part of the reason I'm also involved in this AI Institute project. So another reason is we think the best computer science techniques will become better when they can actually help domain applications. So our focus, like recent focus, are mainly on two areas. One is the cloud computing, and the second is machine learning. And of course, these two areas sort of connected by the big data. So for the computing system part, we're especially interested in the building and optimizing large-scale computing systems, especially for cloud and HPC. And for machine learning, we have been working on various topics, including the AutoML, feature learning, compression, large-scale learning, and other topics. And of course, we have been publishing actively on the top menus in both areas. Things become more interesting when actually you look at the intersections between these two areas. So basically, that's sort of my topic of today. So I will focus on a topic called the machine learning as a service that puts together the machine learning and the cloud computing. So I chose this topic and also because this is closely related to the AI Institute project we're collaborating with ASU and other institutions. Okay, so first of all, what is machine learning as a service? So it's actually very simple. So basically, when you have AI problems, you usually want to build and train your models, and then you want to deploy them into a service, right, to do your tasks. So however, to do these AI tasks, usually you need a lot of machine learning techniques and also computing resources, which is actually non-trivial in practice. So to facilitate this, actually the cloud providers have put everything together you need in like one place. and host them in the cloud to just make your life easier. So that's basically the machine learning as a service. And we can see almost all major cloud providers nowadays provide this kind of service to machine learning engineers and researchers. Okay, so what's like why machine learning as a service is a big deal, right? Why we cannot just use our own computers for doing these AI tasks? There are a couple of reasons. First reason is actually it's greener. So machine learning actually use like a lot of energy and computing resources and emit a lot of CO2s. And I'm not sure if you read about this like a recent paper. It's about how expensive machine learning can be in terms of energy as well as emissions. So basically, the paper says training like 2 big machine learning models can actually cost more CO2 release compared to like an average car's entire life cycle. So that's pretty significant. And if you think about this, if we're training a lot of like models today, right, especially everyone is actually doing some machine learning more or less nowadays, it's almost like equivalent to like putting like millions or even billions cars on the road, right? I mean, it sounds a little bit like Apple, but you got the idea here. So anyway, I think the good thing about using cloud to do this machine learning is cloud actually host all this computation on the like data centers, and most of data centers nowadays use 100% renewable energy, right? So that's why it makes our life, much greener. And the second thing is, of course, for convenience. So this kind of one-stop thing is actually very user-friendly, especially for non-expert. You don't need to actually search and putting together a lot of things. You basically only need to go like one place and you can do everything there. And of course, it's also less like a management overhead, right? In terms of your code, your computing resource, and also your data. And you can start from anytime, anywhere, right? So these are all kind of classic cloud computing advantages. And another thing is about the cost, right? So we know if you want to do machine learning, you do need to buy very expensive equipment. And the machine learning as a service do provide you this very convenient pay-as-you-go, right? Or even in the serverless platform, you can even pay per use, right? Basically, you only pay for how much computation you have, you need to do. And another very significant thing is actually the operating cost. So one example, right, is for UNR, we do actually build like a small like HPC cluster. The equipment only costs like $1.5 million. However, to host this in like a commercial data center, we actually need to pay like 1 million per year, right? So you can see, this is pretty significant since there's a lot of like power, cooling, security, space, right? All these things they needed for hosting this equipment if you want to, build your own clusters for doing machine learning. And of course, finally, it's, if you host on cloud, it's always like up-to-date hardware and software. You don't need to worry about this. And it's also less downtime, right? Like more fault tolerance. Okay, it sounds pretty cool, huh? The question is there any problems? Of course there are, right? Otherwise we wouldn't be doing research on this topic. So in fact, a lot of these advantages I talked here, they are more like potential advantages instead of what's really happening. So these things only give you advantages when you do things correctly. So next, let's take a look at what are the problems I think we have right now with the machine learning as a service. So first of all, I think despite this one-stop convenience, you still need a lot of machine learning expertise to actually design, tune your models, and your hyperparameters in the cloud. So especially for new areas, actually there are very limited amount of resource you can rely on in these platforms. And the second is, even though cloud may eventually maybe go like, for example, serverless, so that you don't need to worry about anything about your computing resource, everything's managed for you, but we are not there yet. And this means you still need to actually have cloud and even computing system expertise to actually manage and optimize all your computing resources. Another issue is the unit price actually of cloud is still very expensive. So we're talking about it might bring down the cost significantly, but this only happens when you actually can manually optimize and manage your system as well as machine learning stuff. So otherwise, it actually can be even more expensive, if you are using these kind of platforms. Finally, I think there are a lot of important features actually missing. So for example, they never give you like any guarantees on the accuracy or how fast your training or inference would be. And if you say you have a budget, they didn't say they can guarantee you to finish anything right within your budget. And of course, there's also some private and security issues. So we can see actually there's still like a long way to go for machine learning as a service to really, to make your life easier. Of course, to better understand these problems and also the efforts we have been made into this area. So we will look at individual stages of the machine learning as a service. The first stage is actually building your model, right? So we honor like, especially if you are domain scientist, like this is probably the most challenging thing if you don't have a lot of machine learning expertise. So to build a model, people usually, of course, use either like a manual approach or use some automated approach to design your model and tune your model. So recently, one of the most promising ways to build the model is using the emerging so-called automated machine learning. And almost like all cloud providers nowadays like emphasize or put a lot of resource and emphasis on this technique. So what's automated machine learning, right, or AutoML? So actually the narrow sense is specifically referred to neural architecture search, basically how you kind of find the best neural architecture design, right, for your specific machine learning problem. However, like kind of Google sort of co-opted this term, right, to like AutoML for neural architecture search, like back in 2017. So that's why it's sort of like a narrow sense. It's AutoML basically refers to the neural architecture search. But of course, nowadays, AutoML has been developed into like a broader concept. Basically, anything you can automate, right, in any process stages during the machine learning pipeline, you can call it AutoML. And this graph basically shows you some of the main things the AutoML actually have been focusing today. And the biggest two things are hyperparameter optimization and also neural architecture search. And there are also some other things, including the automated way to clean the data, to do the feature engineering, and to do the data science, as well as the meta learning. So all of these are actually included under the AutoML scope. So when the first time, right, AutoML has been introduced, there are actually a lot of media coverings, and we know the media usually gives like very high ambitious hypes, right, when they found something new, especially from Google. Right, so it almost sounds like we no longer need an AI expert, right? So AutoML can somehow magically take care of everything for you and solve all the problems we have in machine learning. And of course, such hype is of course like too high, right? For our, so like this moment. And let's take a look at what's the reality there. So well, the reality is, sort of expected, right? We are still pretty far away from these hypes. Otherwise, we wouldn't be learning machine learning today. So the hypes actually are especially far away, right? For domains and applications where the conventional manual-based machine learning techniques have been not well established. So the reason is for today's AutoML, it's not that like really like automated. It still relies on a lot of prior knowledge and experience, for like specific problems, like what are already, like for example, are good architectures, right, for this specific problem. So that's why, it's actually haven't been helping a lot of people yet. And another very important problem is AutoML is actually very or even extremely resource and energy demanding. And let's take a look at the NAS, right, neural architecture search as an example. So this table basically shows you we have like if we want to use NAS to solve problems, we actually need an extremely high dollar cost, high energy cost, a lot of CO2 emission, as well as need like quite a long time to actually design your model. So these are like problems actually put out a lot of like challenges, right, for the AutoML. But of course, we are researchers, right? We love solving challenges. So so in fact, right, there are already a tremendous effort has been made into AutoML. So there's already kind of a lot of progress has been made, right? In terms of like various like tasks under AutoML, and this has already significantly simplified our life in machine learning. So here are just some examples about all these sub areas have been created, right, in just less than a few years. And in this talk, we will sort of focus on the neural architecture search part, since it's one of the most important area under AutoML. And also it's sort of highly related to our AI Institute project. And so for neural architecture search, basically, I've already mentioned, it's basically help you to build your neural architecture like neural networks in like automated way. So sometimes we also call it architecture engineering. So the NAS has been quite actually successful in recent years, and it's actually already outperformed manually designed, based on manually designed models in many AI tasks, such as computer vision, like neural, like language processing. So all these things, they already, demonstrate like its NAS is like a very promising approach. However, the problem with NAS is it's extremely computing demanding. Basically, we know like training a machine learning model expensive. Well, NAS, basically you need to evaluate millions, right, or even billions, models, right? So that's kind of very like scary. And however, we can say, right, like in less than 2 years, we actually has already bring down this cost significantly. Like just in 2018, the state-of-the-art model still needed like more than 40,000 GPU hours, right, to find a good language model. But nowadays, right, this auto shrink basically is our approach, right? We can actually bring down the search cost for the same task to like 1.5 GPU hours. So which is like very encouraging. Okay, so Before I introduce our method, let's just take a look at the deep neural network hierarchy. So usually, deep neural network can actually be divided into like cells, right? So which also we call it like the building block of the neural network. It will including a set of operations. So here basically shows you the topology of the cell, right? Basically, you have like both the node operation and the edge operation. So some NAS method, right? They sort of first fix the cell topology and only focus on searching the best combination of these cells, right? So usually we call this type of method called the cell-based approach. There have been like tremendous efforts and existing works on this topic, and of course there's another line of work that they focus on optimizing the cell topology, right? So which we call node-based NAS, and there's also some like latest work, including the work I will introduce today. So of course, like it's difficult to say which methodology, which path is better, right? So they all have like pros and cons. So for cell-based NAS, the good thing about it is it actually reuse the architectural motifs, right? So basically, if you already find some very good cell topologies, right, in the past, either manually or in an automated way, you can actually reuse it, right? So that you can significantly bring down research cost. However, the problem with this type of method is it's actually limits, right, the search space and limits like the architectures you can derive, and usually this would of course cause like suboptimal performance. And for the node-based approach, right? So of course, since it allows more flexible search, it can actually search for these kind of new building blocks, right? So this is actually very important. And by doing this, you can actually explore, right, the novel architectures. But the downside is, of course, it's very expensive, right? Since there are like way too many combinations for the cell topology. Okay, so let's say, right, like an example, right, about a node-based method. Let's take the state-of-the-art method like DARTS as an example. So it's actually formulates, the NAS tags as, optimizing the mixture weights, right, during the exploration of optimal combinations of all these operations. Or basically, so instead of just look at like a single possible operation between the nodes, it's actually defines a convex combination of all possible operations so that it can, explore their weights and eventually pick, the best one. However, the problem, right, with this method is actually still quite expensive, right, for this type of optimization solution, because first they actually didn't take into consideration of the topology information, right? Basically, they are topology agnostic. And the second is, if you're doing like this, you actually will end up with a lot of redundant evaluation of these subgraphs. That's also brings the cost very high. So what can we do, right? So to solve this problem, actually we have two insights. So first, we want to prune unimportant search space to speed up the search. And second, we want to rely on this topology information to even further speed up the search process. So based on these two insights, we actually developed a new node-based method called auto-shrink. So this graph basically shows you our case steps about our approach. So actually before the search start, we actually first will construct a topology shrink space, which can be, for example, you can use like a complete stack, right, to represent the cell topology, and then once you have that, you can actually random sample different architectures from this initial search, the shrink space, right, the complete DAG, by removing like one edge, right, from the original topology. Then basically you can have a lot of new topologies, like that's has one less edge than the original one. And then you will actually evaluate, right, these new architectures. So of course, to speed up the evaluation, we will use proxy data, right, which means just a subset of the entire training data. And based on the search metrics you are interested in, right? So in practice, in addition to accuracy, people may also care about the latency and the efficiency, right, about the model. And of course, after evaluation, you will pick the best candidate topology, and you will save this for later use. And another thing you will do is you will use this new best candidate to replace the original cell topology, so that in the this is like iterative process. In the next round, basically you are starting with this topology and then cutting like one edge, right, to generate new topologies. And of course you will iterate this process until basically you removed all the edges, right? Then of course you cannot do further shrink. That's when you actually stop. And this is actually like a joint work with Duke, and we published the paper in today's AAAI conference, this year's AAAI conference. Okay, so that's with kind of knowing this like basic idea and basic process. Let's just talk a little bit more details. So let's say we already found this cell topology, right? So next, how can we actually use this cell topology to build the complete neural network? So actually, we just follow the other works in this area. We just stack, right, these cells together to sort of build the architecture, the complete architecture. And of course, you do need to introduce some additional architectural components like the input layer, output layer, and also maybe the residual connections, so that your model can actually go deeper, right? So of course, that's for the convolutional neural network. If you want to use this to search for recurrent neural network, it's also possible. And of course, for recurrent neural network, you only have a single cell, and basically you just put like embedding and decoding around it. It would complete. Okay, so next, just talk a little bit about the search space, right? Since actually search space is one of the most important things in neural architecture search. So for the search space, actually we our methodology supports very flexible search space, right? So basically, here's one example, right? For the initial complete DAG, right? If you have like a 28 edges, like 8 nodes, each with like 2 different operation choices, then your initial search space can be 68 billion different architecture designs for the cell, right? So that's kind of a lot. And that's why, right, we can actually search very flexibly and find like novel architectures. Okay, so of course, right, since the search space is like huge, right, we can say from the example, then the problem is how can we actually manage to deal with such large search space? So the key thing we actually do to achieve this is we call it topology knowledge accumulation. So the knowledge actually accumulates in 2 aspects. So first, by like removing the edges, right, and find which is the best way to remove the edge. Even essentially, you actually remove redundant, edges, right? Redundant operations, so that your model becomes like more refined. And the second is, if you think about this, even though the initial, topology space is quite huge, it's actually shrinking, right, over the process, because every time you take out an edge, that's become a smaller, search space, right? So basically, our search space is kind of intrinsically shrink, right, during the iterations. So that's why, right, even though you start with like a very big one, but eventually you will be quicker and quicker. And of course, we also use, like for example, the K candidates and other things to even further speed this up. So the next, just a little bit, talk about the search objective. And we actually can support like very flexible search objective, right? So in addition to the latency, the accuracy, you can also, for example, add like latency and resource efficiency, right? So for example, you can use this number of max or number of parameters, right? Basically your weights to actually refine your search, so that the model you found not only accurate but also quite resource efficient. So basically, here's just one example about the resource-aware search metric we used in our evaluation. Okay, and so another thing is about the evaluation strategy, right? We talked about we do use the proxy data to speed up the evaluation about different candidates. For the experiments, like experimental evaluation, we actually tried our approach for both CNN and RN. So given the limited time, I won't go much into the details. But the conclusion is we can actually achieve very comparable accuracy or even better accuracy compared to the state-of-the-art works, while we can search so much faster, and also support like various search objectives. The same story for the recurrent neural network. And we also compared our work with the other state-of-the-art method. For example, if you work in this area, probably you heard about the random one, right? Basically, it generates stochastic kind of network connections to find good architectures, and we also beat this by a lot. So finally, you might ask, right, how to determine the search space size and the number of candidates, right? Since we talked about these two seems to be like hyperparameters. We did some evaluation study, and of course shows you kind of it's a trade-off, right? Basically, the larger search space, the more candidates you evaluate, the slower the search process. But this is something you can actually play with, right? And we do found like usually for 8 and 10, right? They have the best trade-off. Okay, so that's about auto shrink. Then now let's talk about what's beyond auto shrink. And of course, we have done a lot of other works in neural architecture search, hyperparameter tuning, and also large-scale machine learning. So I won't go into details because of time, but I think the one big thing right here is about our collaborative AI Institute project. And so here are just some initial insights, right, about how we can actually use NAS for material science. So first of all, I think for material science, we do have some good domain knowledges, right? For example, like the physics, right? And the problem is we don't have much like like architectural motives, right? We didn't actually know have a lot of experience about what are the already good architecture cells, for example, right, for this domain. So that's why I think probably the node-based approach is maybe a good starting point. And of course, we have also been working on like a unified approach to unify both the node and cell-based approach to get like even better performance. And another thing is another very important thing is we do want to incorporate all these domain knowledges, right, into the design process. So for example, like where we can use the domain knowledge to guide the search space, to design the loss function, to get like a better embedding, right, for estimator-based NS approaches. So all these actually what we have been thinking, and of course there might be even more new and novel things we will get along the line. So we are very excited about this project, and we will work together to actually submit a full proposal next year. Okay, so that's basically for the model design part. Next, I would also like to briefly talk about the training stage in machine learning as a service, since it's also been widely used. So first of all, let's see what's so challenge in the training stage. So in practice, right, you usually will have a lot of different scenarios when you want to train a model, especially on the cloud. So say if you are really rich, right, financial freedom, and you have plenty of time, you have plenty of money, you just want to get the best accuracy, right, at like any cost. Of course, that's like one scenario. Of course, a more practical scenario is you probably have enough money, but very limited time. Or another scenario can be you have limited budget, right? For example, if you have a grant, it only gives you so much budget, right, for training the model. But of course, maybe you are more flexible on the time, right? But you still want to get a good or best accuracy. Then the question is, right? Based on all these different scenarios, how can you actually deploy your training job, right, in the cloud? Because you will have like a lot of choices on the cloud, right? For example, there are hundreds of types of instance you can choose from, right? They all have different computation capabilities, but also have like a dramatic like different cost, right? And you can also have more or less of them, right, to form like a distributed computing. So basically, we call this like a scale up versus scale out problem, right? So you might want to say, right, like this is actually a trivial problem, right? For example, if you want to minimize your training time, why not just get the most expensive GPU instance, right? Like it will just give you the lowest training time. But unfortunately, this is actually not true, right? In practice, since we also have this scale out dimension, right? Like a lot of times, it's network bounded, right? Which means it's not always, the more powerful instance you go, it will be better. And another thing is when you have the same budget, right? You can actually have, more cheap instance, right? Than, compared to fewer, very expensive, high performing GPU instance. So our result actually shows, right? Like neither the cheapest or expensive instance they are optimal, right, in some cases. So that's why this is like a non-trivial problem. Okay, so of course this sounds like an optimization problem, right? And there should be lots of existing techniques we can rely on to solve this issue. So the first thing is analytical modeling, right? That's usually what computer science people will do. So actually, we have developed an analytical modeling approach, right, for solving this problem back in 2015, right, even before the TensorFlow PyTorch is born. However, this analytical modeling approach, they usually have strong assumptions on the machine learning models and also the underlying hardware. So given today's fast evolving machine learning algorithms and also the more diversified hardware on the cloud, so this solution is actually no longer like a very good solution. And then how about these classic optimization techniques, right? Say reinforcement learning and Pareto optimization, right? So they sounds like they can also do this. So of course, their problem is they are either too expensive or the performance is not very good. So I actually find that the Bayesian optimization is actually a good candidate. However, for existing Bayesian methods, we do have find some problems. So for example, it assumes like uniform exploration cost, and also doesn't use any machine learning specific insights. So that's why it's still not very efficient in practice. So to solve this issue, we actually developed a heterogeneous cost-aware and machine learning prior-aware a new Bayesian method. So before we talk about our key ideas, let's just take a look at the conventional Bayesian optimization, just in case you are not very familiar with this. So for Bayesian optimization, it actually doesn't need to know the objective function, which makes it like a very general approach. And it actually starts from randomly sampling, some initial points, and then perform the measurements, right? We can see here, the dotted lines, the actual, the ground truth, right? Actual curve. Of course, this is optimal point you want to find. And once with two measurements, of course, you will have like estimated mean, right, about the space, and of course with confidence interval. The nice thing about Bayesian is it can actually use acquisition function to help you compute, right? What's the next point you want to explore, which will sort of maximize your chance to find the optimal point. So basically, that's the conventional Bayesian optimization. Of course, you iterate until you find the optimal point. However, there are two problems, right? We identified. So first of all, like for conventional Bayesian optimization, they treat the search space like equally, right? So basically, all the measurements, right, for any point, they have the same cost. But this is not actually true for the cloud, because in the cloud, right, just imagine, right, when you're measuring the training speed, right, on like a high-end GPU instance cluster versus like a low-end CPU instance cluster, the cost will be quite significantly different, right? Which means in our specific problem, some points are more expensive, right, to measure, and others are cheaper to measure. And the second is it doesn't use any machine learning specific prior, right? So, and we do say there are some opportunities to use machine learning specific thing. For example, so you usually when you go scale out, right? So we will see the speed up usually improves because you will have accumulated more computing resource, but then it actually drops because the networking becomes a bottleneck, right? So that's why you usually have this concave shaped curve, right? So this of course will help you to have a better knowledge of the entire exploration space. Okay, so by incorporating these two key observations, we developed this heter, we name it heter BL, right, with a heterogeneous Bayesian optimization, and basically it uses the constraints, right, from users. Like for example, user can specify what's the maximum time, right? What's the maximum budget they want to use, so that we can sort of provide guarantees for users, right? So that it won't actually overexplore, right, the space. So one example about this overexploration is, for example, right, you may have spent a lot of money, right, to actually identify which is the best deployment choice, but then you will find, right, actually by that point you probably won't have enough money to actually finish, the training even with the best deployment choice you found, right? So of course this would be like a problem, since in practice we do have like limited budget, limited time, right? So to of course avoid these over explorations, we also developed some estimation methods as well as the over exploration protection mechanism. Due to time, I want to go to details about the method and the process. Let's maybe just look at an example, right, so that you give a rough idea, what I'm talking about here. Say like we have like 2 points measure, right, like y1 and y2, and of course the same curve, right, ground truth and the estimated mean about the space. And of course, if you use conventional BO, it will tries to select like a point based on acquisition function. But this point might be just too expensive to explore. It doesn't fit your budget, right? So what our approach doing is basically to sort of push this point to a more conservative point, right? So that it will give you the best result. So on average, we can actually save like 35%, the measuring cost, as well as provide the guarantees for user specified objectives, which are very important in practical use cases. And here is just an overview of the entire system design. Again, we won't have time to go to details, and this work has been published in PDPS this year. And if you are interested, you're welcome to read our paper. Of course, for evaluation, I would also skip due to the time. And of course, the conclusions we do make significant improvement compared to existing state of the art. So beyond the HIT bill, like we have also done a lot of work in machine learning training optimization, and these are all examples. We have done this, and this has also been funded by NSF, the CRI program. And I also hope, right, all this experience and since we got from this project can also help our AI Institute project, since we for sure will do a lot of training right there. Okay, so we probably won't have too much time left. Just very briefly touch the last thing about machine learning serving right on the cloud. So first, what's like a model serving, right? So you might familiar with model design and training, but for serving, right, like what's going on here. So the thing is, I guess, right, you spend a lot of time, efforts, resource to design the train model, right? I guess it's not just purely for fun, right? Sometimes you do want to use these trained models to do, something for you. For example, you want to do classification, you want to do detection, right? So basically, the serving here means you, especially in machine learning as a service, means you are hosting your trained model on the cloud to take requests from users and provide them with the model result. Of course, let's say you want to recognize an image as a cat, right? Then of course the model will return a cat to you, right? And you can also other examples like use Siri, right? So all these things actually have quite different requirements than the training part. So one big thing with this model serving is the latency is like a very critical metric, because a lot of use cases you do have these interactive applications, and also maybe mission critical applications. You do need to get the answer as soon as possible. And of course, to get like low latency is like non-trivial, right? Since nowadays we have like all these like very huge models, they do take time to compute the results. And you might say, right, I can always put more servers, use more powerful hardware, right? And yes, you can do this, but of course the cost is actually can be pretty significant. Remember this kind of model serving thing is not like one-time thing, right? It's more like continuous process, right? Which means all this cost can accumulate. So in practice, people actually using these parallelization techniques to speed up the inference to get lower latency, and this is for CPU, this is for GPU. So since we are running out of time, I want to go to details. But the thing is, how can you actually identify the best parallelization, right, to get the best latency? And of course, existing works, including our own work, right, have used the model-based approach. But you can see nowadays, it's the neural network is just too complicated to model accurately. And of course, some model-free approach, they cannot handle these complex situations due to the stochastic arrival process, as well as a lot of configuration knobs. So our key idea here is actually using reinforcement learning to solve this problem. And but of course, reinforcement learning is not something new, right? And the issue with this reinforcement learning is it's usually quite expensive, and especially right in this kind of almost real-time system, right? Like the latency, we usually talk about millisecond level, right? So reinforcement learning usually takes a lot of time to converge, and when it's converged, probably your workload has already changed, right? So what do we do, right? So what we do is our key observation is actually, if you take a look at the trend, right, of these parallelizations, right? So their latency actually changes rapidly, like globally, right? For example, you can see here, you can from like a very bad one to the optimal one, right? Just in one step. However, we found, right, actually, even though it's globally very random, but locally it's actually very smooth, right? So of course, how can we use this? Of course, this is for the GPU. And how can we use this observation to help speed up, right, the reinforcement learning? So our kind of idea is, since they are pretty smooth, right, you can basically use observed ones and to estimate the local regions, so that you will significantly reduce, right, your search space. So we call it region-based reinforcement learning. And of course, I want to go to details. And this work has been published in the supercomputing last year. And of course, evaluation, I would escape. And more recently, we sort of also made efforts to use the serverless to actually speed up or make it more convenient for doing this machine learning survey. And of course, we published some papers. And excuse me. Finally, before I conclude the talk, I just want to. Oh, sorry. Okay. Oops. I just want to also mention, we have been using this machine learning as a service for some domain applications, like the wildfire smoke, tracking is like one example. We have been sponsored by NSF and AWS. Actually, we know, right? The wildfire is actually one of the major disasters for the West Coast, and this year is especially terrible. And we did use this approach, right, to support
what we're going to see is this movie of looking southwest from the Desert Research Institute, which sits north of Reno.
Okay, yeah, because we are running out of time, I probably will skip some details. Finally, I just want to acknowledge our collaborators in both industry and academia, and also all the talented students in my group who has made all this research possible. So finally, just want to say our goal for this specific topic is want to make machine learning handy for every domain, for everyone. And yeah, that's concluded my talk. And thank you. Any questions?
Hi, Feng, can you hear me?
Yes.
Okay. Yeah, I apologize if the background noise because I'm holding a baby right now.
Oh, no problem.
Very nice talk. I have maybe a question more specific to material science.
Okay.
So the kind of systems that we're dealing with, usually you can think about them as multi-body dynamics, where you have lots of particles interacting with each other, and it's um, it's relatively straightforward, I guess, when you look at the forward problem, which is to simulate the evolution of these particles, right? For example, through DFT or MD simulations. But I think it's a much larger scale problem when you want to learn the dynamics from observations of it. So for example, if you use expensive DFT simulations to simulate the some dynamics of there, it usually it takes weeks of time. But then let's say if you want to speed it up using a machine learning architecture, say a graph neural network or something, then it looks like the capacity of your infrastructure for computing will be much more than if you just want to run a forward simulation. So there's a recent paper where from DeepMind where they simulate a CFD simulation, right? So it's basically fluid running in a box. And then they treat the particle of the fluid as, they treat the fluid as lots of particles, right? And they give an example which is two-dimensional, and they say on a single V100, you can run a learning with a batch size of 2. And then batch size of 2 is pretty pathetic, right? And it's a 2D simple simulation. So for the real 3D simulation they run, they actually use TPU. And it sounds like this is the only solution. I just want to maybe get your insight on whether there will be, whether you will have to stack a lot of V100 or get TPU service, or from your experience, there's some smart design that you can craft out from the hardware side, right, or from the architecture side to make this type of learning possible.
Okay. Yeah. That's a good question. So of course, I'm not have a lot of background on this specific problem, but in general, I think if the speed is your real kind of issue here, like usually, we can do a lot of things. So for example, from the architectural design, right? Like you actually can control your architectural design by specifying, right? For example, the work we have done, you can actually specifying some constraints about how expensive this would be, right? If you think about this, it's basically like a trade-off about how much you can do, right? For example, how many iterations you can do versus in each iteration, how much gain you can get, right? So this is actually a trade-off. Doesn't mean the smaller model, right, will always perform worse. If you think about the work log time, right, maybe they will perform worse in terms of number of iterations, number of epochs. But if you really look at the work log time, it's actually probably not always the case. And another thing is, if the batch size is a concern, we actually have recently been working on the large scale kind of optimizer, right? So where we can actually have like several orders of magnitude higher large batch size compared to conventional or like the typical use batch size for a specific problem. So where we can actually increase the batch size to still maintain the same performance. And of course, you might say, right, so for GPU you might run out of memory due to this large batch size, but we do have techniques that can allow you to like basically the thing is you cannot fit too large batch size into the memory, is you will kind of run out of memory, right, before you synchronize your model. But we can actually accumulate this locally, and just to reduce the number of synchronization. right? Basically, you can actually have a virtual large batch size, right? Even if you have like a very small, GPU or even, CPU, you can still do like, this large batch size supported by TPU. And of course, TPU is actually a good, potential solution, but the thing is, it's pretty much limited to the Google, right? Basically, you're stuck with Google, for the rest of your life if you really, look into the TPU solution. So I think, with our background, we can definitely, solve this problem with GPU or even, CPUs. So another thing about, these kind of problems is you actually can host this on, of course, on the cloud, right? And for example, use our large scale training kind of solution. You probably can find some optimal kind of deployment choices based on your specific budget, as well as how much time you want your model to get the result. I'm not sure if I answered your question.
Well, I think that's a lot of information. Thank you. I have some questions, but I will reserve them for offline.
Okay.
Because this is not.
Yeah, in short, I think we do have a lot of background, in all kinds of angles to solve the problem you have here.
Yeah, let's see from the audience if there are other questions.
Okay, I guess.
So I do have a question, but I'm not sure whether I should be considered as the audience or. So this is going to be a quick question. I think this is a very inspiring talk. So I'm very I see the big picture, the overarching goals, and also the architecture that that we can go to the details. I do have one specific question concerning the architecture search. So the auto shrink method you mentioned is a very nice one, and I think you also mentioned that you can have this cell topology, and also you can have some architecture related to the cells. I think these actual are idea match the material microstructure very well, because in materials we know a lot of physical mechanisms involve different length scales, right? If you talk about mechanical properties, it may start from the fundamental length scale with dislocations, but eventually this gonna propagate to upper level scale. So in this sense, I'm thinking maybe you can focus on, for all the mechanisms on the same length scale, you can put them as nodes for the same cell, but for different length scales, you can actually group them as different cells and consider constructing this, which is quite nice. But one specific question I have is that when you talk about the architecture search, especially the auto shrink method, I think you're starting with a well-known list of nodes, right? So I see that you have a lot of interesting ideas to design the graph or the topology of the cell, but you didn't mention the selection of the nodes. At least I think this is for materials is also a big concern, because clearly you can start with all the atoms in the system. That would be a natural choice of the nodes, right? If you know all the atoms, you can in principle predict all the behavior. But we know this is not possible, because even you have a very tiny amount of material, you have huge amount of atoms. We have to use some kind of reduced dimension representation of all of these degrees of freedom. So my question is that when we do these architecture search approach, is there any method to smartly suggest some selection of, or the best selection of nodes for a system like a material?
Okay.
Is this clear?
Yeah, that's a very good question. Yeah, I definitely understand your question. So basically, you are pretty correct. Like even for this, for example, our auto shrink, even though we already kind of like one step further, right? Compared to most of the state of the art, like we allow flexible define, of the cell topology search space. Actually, you also need to start from somewhere, right? To say like, how to define, the shrink space, right, at the first place. And as you said, there are many different operations you can do. And of course, their connectivities can be even like more tricky, right? So there's not a lot of existing works on this area in terms of automatically identify like based operations for like a completely new domain. But I think the thing here is with our approach, right? We do actually allow like a very fast search speed, like for a relatively large like scope. So basically, even for our current work, we do allow the node to represent different operations. So that's actually can be part of the search space, and no problem. Like of course for this specific evaluation, we of course use computer vision and also like language modeling. These are very well established areas. We do have a lot of existing knowledge. But of course, we also like have like crazy, like low search cost, like 1.5 GPU hours, right? But I think even we increase the search space, right? By incorporating a lot of like like new possibilities, since we are not sure yet which are the best operators and the initial starting point for this new domain. We actually still can make this like a very like manageable like search cost. And another thing is, as I said in the talk, another thing is we can actually use the domain knowledges, right, to actually help even further speed up the search process. I think that's sort of if that success, we can sort of further compensate, right, the larger or undetermined initial good starting point. I'm not sure.
Okay. Yeah. This is a very good answer. Thank you. I think we may talk more offline.
Yeah. Definitely, this is like a very interesting and probably can even inspire some kind of new insights in the whole neural architecture search domain.
Sure. Thank you. Thank you very much.
Okay. Thank you.
Yeah. Thank you, Feng. I think it's about time to conclude the presentation then.
Okay.
Yeah, I want to follow up with you on some details related to the project. Let's set up a meeting for that.
Okay.
Yeah.
Sounds great. Yeah. And thanks again for inviting me for this talk. And yeah, I think we'll keep in touch and looking forward to get really good results for this project.
Yep.
Thank you.
Okay.
Thank you very much.
Yeah.
Thank you.
Thank you.
Have a nice weekend.
Bye. You too.
Bye. Bye.